Hi. Welcome back to our lesson series where we evaluate a design problem of a process to produce methanol from carbon dioxide and hydrogen. We are continuing with part 2 of lesson 2. Before we continue to answer questions 4, 5 and 6 of the evaluation process, let us revisit the design problem to see all the proposals, suggestions and modifications we have done so far. We will continue with the evaluation after reviewing the new process design problem. Actually, we may find out that it is not necessary to continue answering question 4, 5 and 6 as the problem would have significantly changed. Okay. The revised problem so far looks like this. We are feeding a gas mixture of carbon dioxide and hydrogen at mole ratio of CO2 to H2 of 1:3. The feed stream conditions are taken to be at the previously stated conditions of a temperature of 35 degrees Celsius and a pressure of 1 atmosphere. The methanol synthesis reactor operates at a temperature of 230 degrees Celsius and a pressure of 50 bar. So we will need a compressor before the reactor to compress the gas from 1 atmosphere to 50 bar. We may also need a heat exchanger before the reactor. We will see this after doing the compressor calculations to see if we need to cool or heat. Remember, gases heat up during compression. The gas is now fed into a PFR reactor operating at a temperature of 230 degrees Celsius and a pressure of 50 bar. The reactor is a stoichiometric conversion reactor type with the conversion of 100% of the reactants to products. Remember from the previous lesson, Lesson 2, Part 1, that the product stream leaving the reactor at a temperature of 230 degrees Celsius and a pressure of 50 bar consists of two phases, with gas and liquid. This stream will need to be cooled to be 100% liquid before we can pump it. Also, the stream leaves the reactor at a pressure of 50 bar. We need to reduce this pressure to 250 kilopascals before we send it to the distillation column. Before we proceed, let us do ChemCAD simulation of the process to decide on the way forward. The first thing that we will do in ChemCAD is to define engineering units that we are going to use. Click Format on the toolbar and select Engineering Units. We will be using Formal Standard International Units, so you can go ahead and click Formal SI. Change the temperature units from Kelvin to degrees Celsius, and change the units of pressure from Pascal to bar. Next, let us select the components in our process that we know so far. We have hydrogen, carbon monoxide, water, and lastly methanol. Moving forward, we are automatically taken to the process conditions. Let us give the range of our operating conditions, and we will leave the minimum temperature at 1 degree Celsius. We know that our reactor operates at 230 degrees Celsius, so let us change the maximum temperature to 300 degrees Celsius to give some allowance of temperature going higher. Let us leave the minimum pressure at 1 atmosphere where it is. We know that our reactor operates at 50 bar, so let us change the maximum pressure to 60 bar to give some allowance of pressure going higher. ChemCAD automatically suggests a VLE thermodynamic model as PRSK and enthalpy model as mixed enthalpy model, MIX-H. This is based on the selected components and range of operating conditions. We will accept these and not change them. We will not change anything on the thermodynamic model settings, and we will accept the recommendations. Now let us start building the flow sheet. We have the feed. Then, the compressor to increase the pressure of the feed stream to the required 50 bar. Then, we are likely to have a heat exchanger. At this point, we don't know if it is for cooling or for heating. Next, we have our reactor. Remember, it is a stoichiometric conversion reactor type. Now, let us specify the feed conditions. The temperature is 230 degrees Celsius, and the pressure is 1 atmosphere, which is 1.01325 bar. We don't know the feed flow rate at this point. However, we know that, for each 1 mole of CO2, we have 3 moles of H2. For now, let us go with 1000 kilomoles of CO2 and 3000 kilomoles of H2. Let us specify the outlet pressure of the compressor as 50 bar and operating efficiency of 0.75. We can run the compressor and check what is the outlet temperature going to be. The simulation runs and completes successfully with no warning or errors. The exit temperature of the compressor is 709 degrees Celsius. This indicates that we will need to cool this very hot stream to get to the reactor temperature of 230 degrees Celsius. Let us specify the heat exchanger operating conditions. For now, let us state pressure drop as 0 and the outlet temperature as 230 degrees Celsius. We can run the simulation for the heat exchanger. The simulation runs and completes successfully with no warnings or errors. Now, let us provide the reactor specifications. Let's say the reactor will operate isothermally, at a constant temperature of 230 degrees Celsius. Let us choose the key component for conversion calculations as carbon dioxide. For conversion of 100%, fractional conversion is 1. Now let us specify the stoichiometric coefficients of the reaction. For hydrogen it is -3, for carbon dioxide, it is -1. For water, it is 1, and for methanol, it is also 1. The negative sign indicates that the component is a reactant, and the positive sign indicates that the component is a product. We can now run the simulation for the reactor. The simulation runs and completes successfully with no warnings or errors. We can see that there are 2 phases at the exit conditions of the reactor, with the vapor fraction of 0.579. This indicates that we cannot use the pump on this mixed phase stream. Also, the stream is at a very high pressure of 50 bar, and the distillation column is stated to operate at 2.5 bar or 250 kilopascals. We can exploit this high pressure energy to drive the movement of the fluid from the reactor to the distillation column, instead of using the pump. However, this pressure is very high and needs to be reduced to about 5 bar before we can prepare to send it to a heat exchanger and then, to overcome the momentum work and piping friction losses as we transfer the stream to the distillation column. Let us now add a valve to reduce the pressure from 50 bar to 5 bar. We can now run the simulation for the valve. The simulation runs and completes successfully with no warnings or errors. We can see that the stream has cooled down to 128.7 degrees Celsius. The stream is still mixed phases with vapor fraction of 0.7. Let us add a heat exchanger to cool the stream to 90 degrees Celsius as required by the distillation column. We can now run the simulation for the heat exchanger. The simulation runs and completes successfully with no warnings or errors. At 90 degrees Celsius and 5 bar, the stream is in the liquid phase as we can see that the vapor fraction is 0. At this point, I would like to suggest that we eliminate the second heat exchanger and feed the stream, at the conditions of the valve outlet, into the distillation column. This will save the capital cost of the whole equipment, which is this second heat exchanger. Okay, moving on. We will first remove the heat exchanger. Let us change the outlet pressure of the valve to be the same as the pressure of the distillation column. We will come back and adjust this when we are doing momentum balance and pressure drop calculations later. Let us add the distillation column type, tower. This type of column allows us to specify various input parameters that we can come back and change later if we will leave the condenser type at option 0, which is total or no condenser. Let us state the number of stages as 20. Specify feed tray to be 10. Click on the Specifications tab. Select the condenser mode to be option 1, which is reflux ratio. Specify the value of 1. Select the reboiler mode to be option 6, which is bottom component mole ratio. Select the component to be methanol and specify the value of 0.1, as stated in the problem statement. Click OK. Then, run the valve unit. The simulation should run and complete successfully with no warnings or errors. Then, run the tower distillation column unit. The simulation runs and completes successfully with no warnings or errors. If we look at the top product stream, more than 90% of the methanol is in the top stream. If we look at the bottom stream, less than 10% of the methanol is in the bottom stream. Our simulation is complete and meets the requirement of the problem specifications. Coming back to answering questions 4, 5, and 6. There is no need for a pump. There is no need for a heat exchanger. The distillation column operates well at the specified conditions and produces the required product specifications. We are done with the first part of this project. Thank you very much for studying with Tutor.me Open College. Please click subscribe so that you are kept updated with new learning material as it is being updated. If you like this video, also, please click like so that the video is recommended to other learners such as yourself.